will be related.
Any charges is moving?
Any charges if move, some charges are moving, how the magnetism related to the charge. That is LC. What is the current? Flow of electron with in a given time t. Okay. If some electron flows with respect to this, what is magnetism? How magnetism related to this electricity? No.
Same charge.
No. Yesterday I told you and teach you the diagram. Just I asked a simple question of yesterday. What is current?
Flow of charges.
Flow of charges or flow of electron. Okay. I is equal to dq by dt. Q. The Q will flow like this. Which is
potential.
No, potential is applying to it. Potential, if you apply potential V1 and V2, that's a potential. Potential will lead to the acceleration of the electron charge. Acceleration of the charge. That's why now it's very bright. Okay, so where light is very bright. When it's dim, you will not say current is current is drop. You will tell that current is there, but voltage drop you will tell. That means this one is you have no problem, but here it is. Q1 same Q, but V1 delta V, V1 V2 delta V is equal to V2 minus V1. Here V1 V2 delta V is equal to V2 minus V1. So this one is V1, this one is V2. Let us assume, or V3 like this. Same thing. No, we don't know V3 V4. Okay, when it's there, for here it is normal, no full brightness. Okay, here it is full brightness, here it is off brightness. Off brightness immediately you can judge. This brightness you will not have, you will have half of it. It will be off brightness or dim you can put. Why you put off brightness? You can put dim. Okay, full brightness, off brightness. So the potential difference is here it is delta V. 1. Here it is delta V2. So which will have a high potential difference?
V1.
V1. Delta V1. So delta V1 is greater than delta V2. Because now you have a potential. This potential is nowhere related to the potential is acceleration, one of things. But how the charge here? This charge here is it is perpendicular. Magnetic field will be all the charge. Whenever the charge travels, the magnetic field will be perpendicular to the charge. First, no, this is nowhere related to this today's chapter. This is a discussion about yesterday's chapter. I am revising again the last chapter. Again going for this chapter. Now what we are going to electromagnetic induction. So this electromagnetic induction, how it is related? Now first relation is this one. So the charge. This is the flow of current. The current flows. Then how the magnetism will flow? Perpendicular. That's all. This is what I asked. See, for asking one question, for getting one answer, I asked only one question. How magnetism and electricity and magnetism related? Magnetism is always related to the perpendicular to the electricity. Now only you telling that answer that is perpendicular. So for that, how many hours I spent 5-10 minutes? I spent it now to get one answer. I spent 10 minutes now. I went to last chapter, again I revised it, again I came back. Now I spent almost 10 minutes getting one answer. So magnetism is always, perpendicular to the electricity is always, magnetism will always flow perpendicular to the electricity. So this is what the main thing is that if this main thing only goes means, then only we can go for electromagnetic induction. At least write everything now. I is equal to dV by dt. No, d not dV, dq. Current is equal to dq by dt. Okay. In 1860, Henry proposed. In 1860, Henry proposed that electric current were induced in the electric current were induced in the coil. Electric current were induced in the coil. When there is a change in the magnetic field. Electric current were induced in the coil. Electric current were induced in the coil when subjected to change in the magnetic field. So this phenomena in which the electric current is generated by this phenomena in which the electric current is generated by varying the magnetic field. The current is generated by varying the magnetic field is called electromagnetic induction. Okay, so what is the definition?
In 1916, Henry proposed that electric current were induced in the coil when there is a change in a magnetism. So this phenomena is in which the electric current is generated by varying the magnetic field is called electromagnetic induction.
No, that's all. So based on this proposal, Henry proposed 3 experiment. Henry. No, Faraday. Faraday proposed 3 experiment. Faraday proposed 3 experiment. Proposed 3 experiment. Faraday proposed 3 experiment. Okay. So Faraday proposed 3 experiment. Okay. So in this first experiment, what is our aim now? What we say? What we see in the definition?
In 1916, Henry proposed that electric current were induced in the coil when there is a change in magnetism. So this phenomena is in his.
So this is the first part. So I am bringing the magnetism near to it. So experiment number 1. Experiment 1, XP2, XP3. So that means I am having this galvanometer. What is the purpose of galvanometer?
Measure the voltage across the given section.
I can also measure the current also. This is the current flowing. I am showing the deflection. So I am bringing some coil is attached. I am bringing the magnetic field. That means what? When I bring the magnetic field, magnet, what will happen? Immediately the current flows. So when the current flows, immediately that's the I. So immediately you can see the deflection in the galvanometer.
Yeah.
So this is the experiment number 1. So when I first you take first you take this picture. First you take the sentence, then you take the picture. Okay, in experimental 1. In experimental 1. In experiment 1, I'm Faraday, or generally you have to write in the general term only. Bring magnet is brought near to the coil. What happened immediately? Observation of current flows is observed, which is observation of current is flowed is observed, which shows that showed the deflection in the galvanometer. That's all. So how will you write? When a magnet is brought near to the coil, current flows is observed, which showed that deflection in the galvanometer. That is, the galvanometer got deflected means the current flows. If it is not deflected means the current will not flow.
Which shows the deflection in galvanometer.
Which shows the deflection in the galvanometer. In experiment 2, what will happen? I'm attaching, see, this is the battery. I will now magnet is replaced. Magnet I replaced with a coil 2. This is remains same. This remains a battery. Battery means what I am doing to the coil now? I am supplying the power to the things. What I am doing? Then I am moving the shifting it. Then I am shifting it. When there is a shift, what will happen? Immediately the current shows the deflection in the galvanometer, which is current shows deflection in the coil 1 in the galvanometer. That means when it is moved means why it is showing the current?
The power is supplied.
Power is supplied. Power is supplied. The current is moving. When this current is moving, what will happen? The current is it has a current, okay, because it's covered supplied to the battery, but it has a magnetic field. Once it has a current, immediately the magnetic field is perpendicular to the current. So it has a certain magnetic field perpendicular to the current. But that magnetic field, what is doing? This is inducing the thing. But when it is inducing, when it's moving, it's inducing the current. But now when it's kept stationary, it will not induce. Okay? I'm switching on the battery. You can put positive and negative also. Positive, negative. Okay? First I am switching battery. Then I am shifting it. Then it says that the galvanometer will
Shows
deflection. When it shift, that's why I put this arrow.
Okay.
Shifting. When it's shifting only, I'm getting the extra. When it's shifting only, I'm getting the current. now the same strategy I'm going for experiment. Now here I'm shifting same. This is the second and the third is same. Second and third are the same. Only thing second when I will get here the deflection in the galvanometer current shifting. It has to move. It has to move. It has to move away. Either away or near, both the things. But normally we will take away. So normally if we take away, because we kept it close and we shifting away. You write as shifting away. Shifting away. Okay. So when it moves, immediately you get a current. So how will you measure current using galvanometer? Deflection, some deflection. If you get deflection, sir, the moment you got current, we don't want 1000 megawatt current or 1 megawatt, some current, little bit current. Some little bit current is there. Immediately you can show the deflection in the galvanometer. The same thing. What I am doing, this is the same experiment only. What I am doing now? I am pressing. When the same rotating it, I mean both are constant now. But only time I am inserting the rod. This is the rod. This is the rod. What is what it is? It is a rod, iron rod. Iron rod is I am infusing the iron rod. What I am doing? I am passing the current here. I am passing current here. What will I am doing? The rod is inserted. That
inserted in the coil.
Inserted in the center of the coil.
Okay, sir.
Rod is inserted in the
center of the coil.
Center of the coil. Rod is inserted in the center of the coil. The moment the rod is inserted, here the current flows. Current flows. Here the rod is there. Rod, it's iron rod. Okay, it's iron rod means what? It's not connected to the coil. It's not connected to the coil. When they connected to the coil is slightly different. It's just inserted in the center. It's a rod is inserted in the center of the coil. Center of the coil, because that means this is a coil. This is a this is a rod. This is a rod. So this coil and rod is not
connected.
It's not connected. Yeah, correct. So coil and rod is not connected. It's not connected. So that means what? It's not connected, but it's inserted in the center of the rod. Both the coils inserted in the center. So when you switch off it, the current flows. What the current flows? What will do? It induces the magnetic. So immediately the magnetic field generated in the rod. This magnetic field generated will induce the current in the
coil 1.
Coil 1, yeah, correct. This is in coil 2. C1, C. So the magnetic field will be generated. Magnetic field will be generated from the rod. This rod will in turn induce the current in the coil 1. So which shows the deflection in the galvanometer. Otherwise, okay. Now if I remove rod, I am switching on the C1. I am switching on the battery for C2. Now what will happen to C1? I am removing the rod.
The reflection is not.
I am removing the rod. Then switching on the C1. C2. So then what will happen to C1?
Reflection காட்டாது. நியரா இருந்துச்சுனா காட்டாது, பட் தள்ளி இருந்துச்சுனா காட்டும். Both side rods remove. Both
the side I am removing the entire not one side. You can't keep on one side. I am removing the entire from the entire experiment. I am removing the rod. Now I am switching on the experiment. Now I am switching on the C2. What will happen?
Reflection இருக்காது. Battery on பண்ணல. Battery on.
Battery is on. I am switching on the current. That's why I am telling you switching on the current. I am switching on the current, but I am removing the rod. What will happen to C1?
Reflection will not show in the galvanometer.
Okay.
When shifting away only it will show the deflection in galvanometer.
Okay, when the shifting is there only the reflection shows. That's okay. When I switch it off, I am removing the rod here. First I am removing the rod, then I am switching on the C2. What will happen to C1? What will happen to C1?
It will not show in galvanometer.
It will not show the galvanometer because
Only shifting away.
either if it shifted means that go to C2 experiment. If I insert a rod means that's a C3 experiment. But none of the experiment will show direct reflection. But current will flow here in C2. But immediately it will not affect the C1 because it's a flow of thing. Because if it is there means immediately you never shift at all, right? Here you are doing the shifting away. That means you are shifting the C2 away from the C1. C2 from C1. You are doing that shifting process. But some either shifting process or inside you have to insert the rod inside the coil, inside the center of the coil. What? Magnetic flux. Magnetic flux. magnetic flux. The magnetic flux is the rate of change of the rate of change of the magnetic field that flows in a given magnetic field that flows in a given area. The rate of change of magnetic field B, rate of change of magnetic field B that flows in a given area A. Is called in a given area is defined as magnetic flux. Is defined as a magnetic flux. So magnetic field is equal to what is B? B. This is magnetic field. What is B? Huh? No, yeah. This is magnetic flux is equal to magnetic field into given area. So give BA cos theta. You know how you got cos theta, no? So this is a given area. So this is a given area, and this is a magnetic field. So this is perpendicular. This one is perpendicular thing. So this one is magnetic field. This one is perpendicular. So this is the theta. So that is BA cos theta. You know how theta opposite. This is already yesterday, no?
Yes, sir.
So opposite. So that is theta is opposite. Cos theta is equal to opposite by hypotenuse. Where here is hypotenuse? B here. This one is not B. This B is magnetic field. So this direction is hypotenuse. This one is opposite. So opposite divided by hypotenuse. Cos theta.
Up to BN?
Up to BN, 1 2 3 up to N Bn dot An.
B plus Bn.
Bn dot rho. Rho. What is rho? That means why I put rho here instead of A1? I can put directly A1. No. Why I put rho A1? No. Yeah, different area. Different area only A1 and A2. Rho means small area. Small area. It considers small area. So B1 into small area, B2 into small area. So Bn up to small area of An. So Bi A is equal to I is equal to N. That means I is equal to yeah, 0. I equal to 0. So if I substitute I equal to 0, 0, there is no flux at all. Because it could have something like small area flux, no flux at all. But if you substitute, I can substitute to N also. That's why it's written as N. Okay?
Yes, sir.
Faraday's law of induction. Faraday's law of induction. Faraday's law of induction. The Faraday law of induction says that magnitude of induced EMF in a circuit, magnitude of induced EMF in a circuit is equal to the time is equal to is equal to rate of change of magnetic flux through the circuit. Rate of change of the flux. The magnitude of induced EMF in a circuit is equal to rate of change of magnetic flux through the circuit. Rate of change of magnetic flux through the circuit. Rate of change of
magnetic flux, sir.
Rate of change of magnetic flux through the circuit. Rate of change of magnetic flux through the circuit.
Yes, sir.
Okay, so number of turns in the coil. So the what is the magnetic flux? Huh? Huh? No, Faraday law of induction. For Faraday law of electromagnetic induction, magnitude of
Induced EMF in a circuit is equal to the rate of change of magnetic flux through the circuit.
rate of change of magnetic flux. Rate of change of magnetic flux means dx by d phi by dt. That is the rate of change of magnetic flux. Magnetic flux means rate of change means what? The flux changes with respect to time t. That is the rate of change of magnetic flux. So the induced EMF is equal to rate of change of magnetic flux with respect to time t, and E is equal to n by d phi dt, number of turns of coil. Number of turns in the coil. N is equal to number of turns in the coil. Lenz law. Lenz law. Lenz law. The polarity of induced EMF is such that the polarity of induced EMF is such that polarity of induced EMF is such that it tends to produce a current. The polarity of induced EMF is such that it tends to produce a current the polarity of induced EMF is such that it tends to produce a current which opposes the change in the magnetic flux, which opposes the change in the magnetic flux that it produces. The polarity of induced EMF is such that it tends to produce a current which opposes the change in the magnetic flow, which opposes the change in the magnetic flux.
Yes, sir.
Okay? EMF, electromotive force. So flux is equal to B L X. L is the length, X is the breadth. L into X, length into breadth. L into B. So B is the magnetic field. D is the magnetic field. So magnetic field into flux. Flux is equal to B L X. So E is equal to my rate of change of flux with respect to time t, which is minus dou by dou t. Dou by dou t is equal to BLX. So BL into dx by dt. Dx by dt was what? Dx is by dt is rate of change of displacement with respect to time, which is velocity. BLV. So Q is equal to W is equal to Q BLV into is equal to force into distance. What is equal to force into distance, which is force is this one. The flux is what we giving in the electric flux. The flux, this is flux, but now we want total work done, which is force into distance. So this we are taking as a force, which is electric flux is taken as a force. Total force we calculated. So which is BLV into Q. Q is the charge. So E is equal to W by charge is equal to BLV. So F is equal to Q into V plus V into B. If we assume velocity is 0, then what will get? Q into V plus Q into B. No, not here. QV, because velocity is 0. When it's moving, velocity will be there. If it's not moving, what is the when it's stationary, when it's at rest. When it's at rest, V is equal to 0. So when it's 0, force is equal to Q into E.
Force equal to Q into E.
Q into E plus Q VV. But V is 0. When the V will be 0, when it's at the displacement, when it's not moving. When it's moving, you have some velocity. When it's not moving, 0. So it's 0. This one is 0.
Sir, minus rho by dt, yes, sir.
Minus rho by dt.
Okay, sir.
Because the minus rho by this is not this is d, not d. Rho. Taken?
Yes, sir.
So E is electric field is equal to rate of change of flux with respect to time t. E is equal to IR. So current E is equal to IR, which is E is equal to IR. Electric field is equal to IR. So rate of change of current into R into R. So electric flux is equal to it's del Q. Rate of charge. Rate of change of charge is given by rate of change of flux with respect to its radius R.
R is radius, sir.
R is radius.
Del Q is rate of charge.
Rate of charge. Total rate of charge is equal to rate of change of flux divided by R. First,
Yes, sir.
then eddy current. Eddy current.
Eddy current. Yes, sir.
Okay, eddy current. When a piece of conductor is subjected to the when a piece of conductor is subjected to changing magnetic flux. When a piece of conductor is subjected to the changing magnetic flux, what is the example of piece of conductor? Conductor. Example. Yeah, not nickel. Okay, nickel also you can take, but Feminine one we used to have only copper only. Copper is a dominant pair. Where it goes the copper is dominant. So you have to tell immediately copper. Iron, nickel, cobalt is a second example only. Prominent example is the copper. Secondary example is iron, nickel, cobalt. So the piece of conductor means here refers to what?
Copper.
Copper. That's all. A piece of copper is subjected to changing magnetic flux. A piece of conductor are subjected to changing magnetic flux. A piece of conductor are subjected to changing magnetic flux. Induced current are produced in them. 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 Induced current are produced in them, and this current is called eddy current. This current is called eddy current. Okay, eddy current has a following advantage. Eddy current has following advantage. So eddy current is applicable in first is braking in trains. Electric brakes in the train. Braking system in the train. Braking system in the train.
Electric braking.
No, just braking. Not electric brake. Just braking system in the train. Braking system in the train. In the construction of the meters, electric meters. In the construction of the electric meters. In the construction of the electric meters. And induction furnace. Induction furnace. And in the measurement of in the electric power meters, you will be finding
Measurement of?
no, not measurement, just electric power meters. You while getting into star cast, you will be noticing, right, that meters. Why it is kept? That meters is kept. No, when in here, when the star cast is there, in the entrance you will find a big board. That electric board you will find. Then they will keep the meter. Why do you wait?
To
calculate the current. So that's a applicable thing. It is used to the electric power meters. Electric power meters. Okay, so now we go for inductance. Inductance. The electric current, inductance, can produce electric current can be induced in the coil. The electric current induced in the coil. The electric current induced in the coil electric current that is induced in the coil by the rate of change of magnetic flux produced in the another coil. By the rate of change of magnetic flux produced in the another coil. Hence, rate of change of flux is directly proportional to the rate of change of flux is directly proportional to the current. Rate of change of flux is directly proportional to the current. Rate of change of flux is directly proportional to the current. Now, what is the sentence I gave in the induction?
The electric current can be induced in a coil by the rate of change of magnetic flux produced in another coil.
No, it's magnetic flux in the other coil. Rate of change of magnetic flux in the another coil. Yeah. What it denotes? Rate of change of magnetic flux produced in the another coil. What it denotes? That experiment 1, 2, 3. No, otherwise we can put it the rate of change of the due to the external effect of the magnet. Not you can rewrite. Okay, rewrite. What is that one?
The electric current can be induced in the coil
due to the change of the
magnetic flux.
Due to the change of the magnetic field. Just put magnetic field. Magnetic field. You can put. You can take now the first experiment. Out of 3 experiments, you can take the first experiment. What is the first experiment? We are having the coil here. We are bringing the magnet here. What we do? We are just bringing. If you move the magnet, if we move the magnet, what will happen? Immediately the current will be produced in the
galvanometer.
No. Current is produced in the coil, not in the galvanometer. Galvanometer shows the deflection. That means galvanometer shows the deflection means current is produced in the coil. If the current is produced in the coil, galvanometer shows the deflection. There is no current is produced in the galvanometer. Galvanometer shows the deflection. That means they are measuring the current. When this is what is experiment 1 tells them? Experiment number 1. Experiment number 1. Yeah, experiment number 1. What it tells?
A magnet is brought near.
A magnet is brought near to the coil. What will happen now? Huh?
The magnetic field will absorb.
No magnetic field. No. No. No magnetic field. How magnetic field will affect? When the magnet is brought near to the coil, what will happen? You can see the deflection in the galvanometer. That is, the current is produced, so you can see the deflection in the galvanometer. So this is what the experiment 1 tells. Now this is now you go for induction. Now you go for induction. This is nothing but the just a law. A law is derived from the experiment. First they will do the experiment. From the experiment they succeeded. They will derive the law. So that is this induction. So now now you can derive yourself now. Okay, you can perform some experiment and derive the equations result. So okay, the electric
current can be induced in the coil due to
change in the magnetic field. Due to change in the magnetic field. Due to change in the magnetic field. you taken that right now? You have taken no. What is what do you did?
The electric current can be induced in the coil due to change of magnetic field produced in another coil.
No, that I was asked to remove. That only I asked to remove. Produced in another coil, you have to remove. Everything you have to remove. Okay, you tell me what you written? The
electric current can be induced in the coil due to change in the magnetic field.
Due to change in the magnetic field.
Hence the rate of change of time is directly proportional to the
Rate of change of flux.
Flux is directly proportional to the current. Current. That is this.
Sir, what about the rho I by rho d, sir?
Rho I by rho
Rho
t.
t.
That is flux is directly proportional to current. Rate of flux means change of flux with respect to time t. So the rate of flux is directly proportional to rate of change of current with respect to time t. Then n into flux is directly proportional to current. What is n?
Number of turns.
Number of turns in the coil. Okay, take it.
Sir.
So now next is our two types: mutual inductance, self inductance. Mutual inductance and self inductance. Mutual inductance and self inductance. I will be taking one small coil. C1 is a small coil, C2 is a bigger coil. So the distance from the center of the coil to the extreme of this coil is R. So this total length is L. So M is equal to mere. Mere is a permeability of a medium, permeability of vacuum.
Permeability of medium is the vacuum.
Vacuum. So N1 and N2 is number of turns in the coil C1, number of turns in the coil C2. R is the radius from the center of the small coil to the extreme out of the second coil. Extreme out of the second coil. So edges of the to the extreme out of the second coil. This is the center of the small coil. To the extreme out of the second coil. L is the length of the total length.
Okay, sir.
So magnetic induction is given by M is equal to near.
So this is mutual induction or
Mutual induction. No, this one is mutual induction. M. This is mutual induction. This is self induction. So, what is M? What is M here?
mutual induction.
Mutual induction. This one is self induction.
Self induction.
Total EMF is equal to self induction rate of change of current minus IM di by dt.
Rho I by rho.
Rho I by rho t. Everywhere rho I by rho t. Rate of change of current with respect to time t. Rate of change of current with respect to time t. Okay. Now AC generator. You know very well what is the purpose of generator. Normally they will use in the shops because they have to billing the especially in the supermarket. Why? The people will come here, do the consumption immediately. They have to do the billing service. So normally it will do it. They will do in the shops. So what is the purpose of generator?
It supply current during electric current illada podu power supply pannu sir.
To generate the current. Simple words. That's all. You have to put in the simple words. So the generator is nothing but the generation of the current. Generation of the current during an using an external using an other source, using some external source like petrol or diesel, using some external source, using an external source like petrol or diesel. Using an external source, petrol or diesel. Phi is equal to BA cos theta is equal to BA cos theta is divided cos theta. It's like Q, it's not Q, cos theta. Okay? Divided by BA cos omega t. So E is equal to minus n d phi by dt, which is nothing but n by NBA d by dt dou by dou t cos omega t. So definition of cos omega t is sin omega t into omega. So E is equal to NBA omega sin omega t. Now E is equal to E0. That is NBA W is equal to E0. So E is equal to E0 sin omega t. E is equal to E0 sin omega t is replaced by 2 pi nu t. What is omega? Here? Angular frequency.
Angular frequency.
This one is linear frequency.
Which one, sir?
Omega nu.
Mu is.
This one is angular frequency. This one is a linear frequency. So omega is equal to 2 pi into nu. Omega is equal to 2 pi nu. This is theta, omega t. Omega t is nothing but equal to E0 sin theta. If I substitute this value theta means 90 degree. 90 degree means what? 90 degree.
Right.
Right.
90 degree. 90. Sin theta value substitute 90 means sin 90 means what? No, that's okay. No, I don't want that value 1, 2, 3. What is physical meaning of sin 90? 90 degree means?
Right.
90 degree means the coil now, this coil. Okay? Coil. The coil is now perpendicular to the magnet. 90 degree. Then 180 degree. 180 degree means what?
Straight.
Linear, something like linear position. But instead of perpendicular, it's coincident plane. That is linear coincidence with the plane. Coincidence with the plane. So that means the coil is now coincidence with the plane. This is the coil. This is a coil. This is perpendicular. Perpendicular 90 degree means how it will be now coil. Like this. It will be like this. No, because the coil and the magnet are perpendicular. When it's at 180 degree means what? It coincides with the plane, which is this magnet and this plane, which is 180 degree. Then 270 means again inverted. After again 360 means again coincides with the plane. So which is the maximum value here? 90 degree. So when it's 90 degree means it has maximum value. So this theta only we are substituting as omega t. See theta versus omega t. So sin theta, if it is finally this value, we can substitute as you can take E equal to E0 sin omega t. You can take it as E0 sin theta. So E0 sin, so that only we replacing omega value, then omega value we are replacing with 2 pi nu. So but sin theta, E0 sin theta, what is when sin theta 90 degree only the current induced EMF is maximum. Then when it's at 270 also maximum, but is in the opposite direction. That is, this is positive. This will be negative. Same as this point, and this point are same. This is maximum current, here also maximum. So then what I can write here? What I can write here? Yeah, E max. I can write as E max. That means this is the point where I will get the maximum current. Yeah, it's not so. So
Individual EMF, sir.
Induced, not individual EMF. Induced EMF. EMF, that is output of the current is nothing but induced EMF. This is Emax. That means Emax means what? This is the point where I will get a maximum current. That's all. Then the same trend they will ask at 180 degree what is the output of the current? What do you write? 180 degree. Huh?
Maximum.
Zero.
Yeah, zero. See, this is the current. This is the current induced. Okay, current induced at 90 degree. At 90 degree means the coil is perpendicular to the magnet. When its coil is perpendicular to the magnet, the current is this is a maximum current I will get, which is Emax. Now the current goes to this point.
Yes,
What is
sir.
this point?
Zero.
This point is zero. This angle is 180 degree. But the current produced is
Zero.
zero. After the 20 is going in the opposite direction. Again it's producing here. What is the maximum current here?
Minus Emax.
Minus Emax. The maximum current is produced in the opposite direction. So the Emax, this also Emax. This also Emax, this also Emax. This one is positive, this one is negative. So this produced. Then again 380, what is the current produced?
Zero.
Zero, that's all, because it's going this way. Okay, that's all. Take 5 minutes break. We go for another chapter. Okay.